The title of my presentation is Deep-net-derived surface estimations of natural scenes predict voxel responses in scene-selective cortex. So our motivation is that there's evidence for different brain regions specialized for processing scenes versus isolated objects. We know much more about the format of representations in early visual areas and even object-selective cortex than in scene-selective areas. One important and hard to study question is how and whether our visual system represents the configuration of major surfaces of a scene. Some recent work has made headway in this question through constructing virtual 3D environments, which allowed them to model voxel responses based on ground truth 3D characteristics of scenes. First, in this work, we wanted to ask if we could have similar success with naturalistic scene images and verify that the earlier results also hold true in something closer to the real world. And then second, we wanted to find a way to reduce the barrier to entry for studying 3D surface representations and hopefully help to close this gap between what we know about processing isolated objects versus scenes. So our main approach is going to be to build voxel-wise encoding models of scene-selective cortical responses with the idea that the better we can predict these responses, the better we understand what a region of the brain is doing. We used publicly available fMRI data, the BOLD 5000 dataset. They presented images to participants in a slow event-related design with 10-second long trials, and I chose the 1,000 images from the set that were natural scene images. There were 3 participants who had all of the scene trials, and the dataset also includes scene-selective VOIs. And like a lot of fMRI datasets, these stimuli didn't have ground truth information about the 3D spatial layout of the scenes. So I'll show you how we solved this problem. So I used 2 DNNs trained to output the distance and surface direction info, and these were from the Taskonomy project. So basically, we just inputted regular RGB images that were able to output estimates of the distance each pixel was from the viewer. So that's here on the left, and then also the direction that the surface in each pixel was pointing. And we weren't sure how well this would work at all, since there were some differences between the images the networks were trained on and the images that we wanted to estimate for. But it looks like they did a good job. So here you can see that in this estimated distance map, the closer pixels are darker, and that corresponds pretty well to how things were in the image above. And then in this estimated surface direction map, the R, G, and B channels correspond to cardinal directions, making different directions different combinations of these colors, and those look reasonable as well. And it turned out we were able to get 978 reasonable looking estimates out of the original 1,000 images without any visible artifacts. And this is how we turned those maps into the predictors for the encoding model. And if you're familiar with this previous paper, it's similar to their model, just with fewer features. So we start with the distance map and the surface direction map of each image, and we make one long list with each pixel as a single value. And the features are the proportion of pixels that fall into each combination of 3 possible distance bins and 9 possible surface direction bins. And that gives us a total of 27 features for this model. I've highlighted the prediction performance of this model in scene-selective regions, and you can see we're able to significantly predict responses, even using these estimated 3D features, even on naturalistic images. I did hypothesis tests for individual subjects by creating a null distribution by shuffling the image labels of the held out data. So here, the stars mean that this information is significant for all subjects, and then the 2 out of 3 is the number of significant subjects for the ones where not all were significant. For those who are interested, I can talk more at my poster about variance partitioning results versus a 2D Gabor wavelet baseline model. And some takeaways that I'm excited about are, first, even for naturalistic images, scene-selective areas care about these surface properties. And then also the fact that we can estimate the 3D info of a scene using DNNs means we may not need to construct artificial 3D environments to study the 3D properties that scene areas care about. And I'm extra excited. This means that we're able to take advantage of existing large-scale data sets and hopefully make it much easier to make more progress on these questions. And if you have any questions about this work, come by my GatherTown poster, and here's the info below.